LLVM. Oh, okay, let's start again. Hey everyone, welcome to our talk about the LLVM OpenMP ecosystem. We're going to give kind of an overview about lots of things that have happened and are currently happening in that have been in the making for the last few years. So there will be user-centric details, there will be technical details, there will be OpenMP standard things. It will be kind of a variety of topics presented by multiple people, so we'll switch hosts throughout. Obviously, what we are presenting here is not necessarily done only by us. This is really a community effort, and there is lots and lots of people involved. We listed a few here from academia, industry, and our power users that give us a lot of feedback about like what works, what doesn't, and so on and so forth. And we are just kind of presenting the state. That doesn't necessarily mean the people that present something are the only ones or the ones that work on these things. It's more of a organizational thing. If you are interested, reach out, and can we go back one second? There is a link on the slides here, and there will be links later on. We have various kind of meetings. We have a discourse for LLVM with an OpenMP subforum, and we have office hours. So there is various ways to get in touch. There's the link here is for our weekly meeting that happens every Wednesday. Everyone is welcome. It's more on a technical side, but you should feel free to join that, especially if you're interested in working on or with LLVM OpenMP. Okay, let's take a little bit look at the introduction and where you would start. So if you want to use LLVM to do OpenMP offloading, which is probably the OpenMP use case that most people are interested in here, nowadays you only need a single CMake command to make that happen. So the CMake command is kind of listed here, at least the minimal version. What you do is you enable Clang as a project, and you enable OpenMP as a runtime. And then you invoke CMake, and then afterwards make, and you get a Clang that is able to offload to AMD and NVIDIA in GPUs and the host CPU. There's a lot of CMake options that are immensely useful if you work with or on LLVM and LLVM OpenMP. There's a few listed here with regards to build type, assertions, CC cache, Ninja, and so on. But I would recommend to look at the Getting Started documented LLVM webpage and the support and FAQ on the OpenMP LLVM webpage, which basically says how to set a default architecture for your GPUs and gives you troubleshooting tips and so on and so forth. So those links are really, really helpful if you want to get started building your own LLVM. Now, there's a couple of features for HPC developers that LLVM offers, and there's a couple of features that are missing right now. HIP and SYCL support in the LLVM community version are not as good as we want them to be. The vendors, the respective vendors are kind of working on that and upstreaming things as we speak. AMD and NVIDIA GPUs can be targeted with OpenMP offloading. Intel, not yet. That is something that we're kind of still is on our to-do list. So if people are interested in that, feel free to reach out. We have a couple of tasks that need to be done. OpenMP 5.0 is supported almost entirely, and it's also well tested with a lot of priority on offloading, obviously. 5.1 and 5.2 features are available selectively. And then there is a web page on the Clang project that tells you exactly what works and what doesn't, and how, like, what you can expect to work. But 5.0 and a lot of 5.1 features will work nowadays. Let's go to, yeah. So this is just a slide, as it says here. Screenshot me if you're interested. If you want to read more on these things, if you want to see how this is actually all made, if you want more background and technical details than we can give in a talk like this, go for the papers. I mean, there is this is a selection of papers from the last 3-4 years that give you ideas on how all of these things are actually working. And you see a way to find them. I mean, these are the titles. If you put them in Scholar, you will be able to find these. Next one is similarly, again, one to screenshot. These are resources that are useful for beginners. So the OpenMP LLVM org page, as I said before, has an FAQ, has information about remarks, about runtime design, environment variables, lots and lots of things that are useful. We also have a bi-weekly office hour for LLVM and LLVM OpenMP that you can join. You can join in, you can come with your own code, you can ask any generic question about LLVM, about OpenMP. It's 1 hour office hour. Feel free to share that with people. And then there's various presentations online. This is just 2 of them about LTO and JIT support, compiler's view of OpenMP, and at the various meetings and conferences that have been taped, you can find more of these on YouTube. Okay, now if people think about OpenMP and LLVM, what they usually think about is the front end part, where you have Clang and now, or like nowish, Flang, the Fortran compiler, or the Fortran front end. They have these OpenMP parsers that parse these pragmas. They have a semantic analysis for these pragmas, that everything kind of is nested all right and you use the right things. And they have a code generation for them. That is the classical idea of what OpenMP is inside of a compiler. But in fact, OpenMP and LLVM is a lot more. For one, we're transitioning to an OpenMP IR builder, which is front-end independent and helps people to generate the LLVM intermediate representation for OpenMP constructs. The big benefit is not only that you can reuse this from Flang and Clang, but also languages that are not necessarily C, C++, or Fortran, that don't actually have OpenMP, can use this to opt into the OpenMP environment, offloading environment, parallelization environment. So if you're working on Chapel, for example, you can use this to generate offloading code that is then target independent. In addition, OpenMP obviously comes with runtimes. So there is the classic libump, which is a host runtime, and which is what you would expect for host parallelization. It does the tasking, the parallel threads, all of that stuff. And then there is libump target and the plugins, 1 plugin per offload architecture. They are responsible for offloading support, but they're also host runtimes. And then there is the device-specific runtimes. Those are the ones that we embed into the device code of the application to provide the OpenMP support on, let's say, a GPU. So there is one for each architecture, basically, potentially also for the sub-architectures. And finally, one new thing that LLVM offers that is kind of unique also with regards to OpenMP is a specific optimization path that is OpenMP aware. And that path understands OpenMP, understands the runtime calls, understands semantic, parallel regions, tasking, and so on. And it performs specific high-level host and device optimizations. And through that one, we really gain the performance necessary to compete with other models, even though OpenMP by default is more expressive than the kernel languages. So this path kind of transforms the expressive OpenMP into something that really runs fast on a GPU. And we'll see some examples what it does later on. That was my initial part, and I'll give it to Joseph now.
Okay. Hey everyone, I'm Joseph Huber. I work at Oak Ridge National Laboratory, and to start off, I'm going to be talking about some of the work we've been doing to improve the handling of like linking device code and static libraries. So next slide, please. So static libraries are very common for building, large applications. And previously, LLVM did not support static linking for OpenMP offloading. And this created a major problem for, certain applications that made heavy use of these static libraries that wanted to, port over to, using the GPU through OpenMP offloading. So we've done a lot of work to support static libraries for offloading using what we call the new driver, which is basically a way that we generate the code and then link the code that is executed on the device. So now, compared to how before, device code is just embedded into the host to create a fat binary, and we handle the linking using a special offload linker. So next slide, please. So one useful or interesting thing about static libraries is that static libraries are normally imported lazily. That means that the symbols in a given object file will typically only be pulled in if they're actually used in the application you were trying to link. And we can use that semantic behavior here to basically have someone create a generic library that could contain device code for many different target architectures, such as SM50 or SM80, and then we can just put those all inside of a single offloading library, that is, in a single static offloading library. So you can see the examples here, we can simply compile this library with these options to create the static library. And because of the semantic stuff, we can say, oh, the user for their actual application only targeted SM70, but we have a library that provides all of these different architectures. We can then pull out the one we need and link the user's code. So this allows us to actually provide very expressive libraries to provide support for various things on the GPU without needing to worry about sub-architectures. And we'll also have other solutions for that later with JIT that you'll see. So next slide, please. So this is a very high-level overview of how we handle offloading compilation now for OpenMP. So if we have our OpenMP source files with OpenMP offloading, we will then use Clang to create the IR for both the host and the device. And for the device, we will use the vendor tools to create a device object that will then be embedded into the host object along with where we compile the host IR. Now, where this really breaks from how we used to do things is that we use a single offloading linker, which we call the linker wrapper, which basically pre-processes all of these host objects that can contain device code and sees individually, oh, does this have some code that I need to link for the device? And if it does, then it performs the appropriate device linking action and then will embed it so that libOMP target can access it. So next slide, please. And just real quick, this is how we do the overall embedding of device code. So again, we have our input files, and then we will create a device object for each active offloading tool chain. So if you're offloading to NVPTX for SM70 or whatnot, you would have a tool chain to generate that device code. When we finish compiling for that, we just embed it into the host object, and then it will behave exactly like any other host object. So you can put it in static libraries, you can do relocatable linking, you can do anything with it. And if you actually crack one of these open, what you'll find is a section table that contains two special sections we use. One is the .LLVM.offloading section, which contains the actual embedded device code, and the OMP offloading entries, which contains the kernels and globals that we need to register. So that is all used internally when we do the linking. And as we see in the section contents, it can either be a bit code or an object, which brings us to the next topic of LTO support. So since we were doing this, we wanted to support link time optimization. So what is link time optimization, or LTO? So compilers normally optimize only a single translation unit or source file at a time. And this kind of causes problems for a lot of optimizations that maybe wanted to see the full scope of the program, like some constant was defined in file A and then used in file B. Because those are defined in different files, we can't do like constant propagation or various other things. Additionally, this prevents us from inlining or getting rid of the overhead for like GPU calls, which is very expensive. So LTO solves this by allowing us to run optimizations on the whole program instead. And LLVM does this by simply emitting and linking LLVM IR instead of like a standard ELF object file. And what happens is the linker will then pick that up, see that it is an LLVM IR file, will then link all the LLVM files it found, run the LTO backend, then add the output object file to the original linking job. And we have simply ported the same support to now work on the GPU for OpenMP right now. And you can see an example here where you do -f offload LTO, and you will use LTO for the GPU. And we really recommend this, especially for very large applications that have many files. You can get pretty good performance increases using this, as we'll see later. So next slide, please. So this is just a very high level overview of the linker wrapper I mentioned previously and how it supports link time optimization. So as mentioned previously, the linker wrapper essentially wraps over the normal linker job that the compiler would have run, except now we take all of our linker input, we scan it for objects inside of that .lvm.offloading section and extract them. And then we will see if it is a device bit code for some sub-architecture or a device object for some sub-architecture. If it's bit code, then we can do what I mentioned previously and link them all together, run a single optimization on them, and then get a device object file, which we will then just run through the vendor linker, whatever it is, to get the final device image. Then we will run a wrapper phase, which basically just creates the necessary registration code so that libOMP target can actually register that image with the runtime. So next slide, please. And this is the types of performance increases you can see that we observed when applying link time optimization to a few applications. So on the left, we had the Thermo 4 FPM application, which once you started getting into reasonably large iteration spaces, we saw a pretty marked improvement over the non-LTO version with about a 2x increase. And similarly, on the right with the mini MDoc application, we saw pretty good improvements in every case, no matter how we configured things with LTO. So I would highly recommend, if you are compiling a large application, to use the support if you have an up-to-date LLVM version. So next slide, please. Okay, and the stuff I mentioned previously is very useful for OpenMP, but we can actually extend this to the other offloading languages. So other offloading languages such as CUDA and HIP, we can make them use the same scheme that we use for OpenMP now, where we embed things in that LLVM offloading section and use the linker wrapper to link them. And what that lets us do is then put everything into one big binary blob, so we can then link OpenMP and CUDA code together, for example. So we have these Clang invocations, which show how you could, using this support, compile both OpenMP and CUDA together, and then have OpenMP call functions defined in the CUDA, or vice versa. So this isn't upstreamed yet, but it should be working relatively soon. And this also will allow CUDA to make use of the great features I mentioned previously, like static linking and LTO. So next slide, please. And again, this is very similar to the previous image, but it shows generally just what we will do to actually support this offloading language interoperability. So again, we have all of our linker inputs, we scan them for the embedded device files, and then we will see if, hey, if this is CUDA and this is OpenMP, but they're compatible, sub-architectures, then we can link them together to create one big image, and that will allow your CUDA code to call your OpenMP code. And then once you get this device object file, which contains the final linked image, then we will simply run it through both a CUDA registration wrapper and an OpenMP registration wrapper. And then both of those will exist together inside your final application. So you can execute, it'll offload to CUDA and OpenMP at the same time. And just one caveat about this is that the device images will be distinct in this case, and that means that you will not be able to access some internal state from CUDA if you're using OpenMP. So like a device global variable, you wouldn't be able to pull the value in that. There's some work we've been looking into to address this, but this basic support goes a long way, I think. Next slide, please. So mentioning the OpenMP runtime previously, we try to provide a lot of debugging and information features that you can query inside the LLVM OpenMP runtime, or for OpenMP offloading. So one of the things we really tried to do is improve it to where you get at least some error message. So previously in older releases of LLVM, if your application failed inside of the target region on the device, it would just give you just one message that said the target failed. It wouldn't tell you why it failed or where it failed. You just need to figure it out yourself. And we've been moving to improve this. So for example, we have some code on the right here where we are doing some just simple sum reduction, and we will take this location information, excuse me, we will take this and execute it, and it will actually fail. And the reason it fails is because we didn't map this array in. So if we compile this, we can then get the information and see, hey, an illegal memory access was encountered. And that's basically just a seg fault on the device. So when this fails, you'll see why. It'll tell you when this, sum.cpp 5.1 if you had the debug information enabled, and then it'll usually tell you to go to this website, which has a lot of information. Basically what I'm explaining to you right now for getting more debugging information. So next slide, please. So another thing we support is getting actual information from the runtime itself. So when your application is executing, you might want to see certain things that only libomptarget target knows, such as, which things are being mapped to and from the device, which kernels are being executed, how many threads or blocks are being used. And we support this with this libomptarget target info environment variable, which takes a bit field, which lets you individually enable different pieces of information that you might want to see. So we took the same example as previous, except added the missing mapping clause so it will work now. And you can see when we compile it again with gline tables only, we can then enable it with this libomptarget target info to set these bit field flags. Then when we run it, it will say, we are entering this OpenMP kernel with these arguments. You can see which arguments were implicit or explicit, how many bytes were copied, what the original name was. And then you can see the actual memory accesses and transfers that are happening on the device. And then finally, you can just see which kernels were launched and how many blocks and what mode it is. And I'll talk more about the SPMD mode later. So next, please. So finally, those previous two solutions work well for debugging on the host. But if you want to debug in the device itself, it's sometimes helpful to use what we support for actual runtime debugging. So the OpenMP device runtime supports debugging inside itself. And the way we do this is by having a global that is set by this -f OpenMP target debug flag, which will then configure what your debug level is at compile time. And if you didn't set it, then it will be 0, and then all of the compilation steps will be trivially dead. So because of that, we can then support this, free debugging basically, because it'll all be optimized out at runtime. I mean, at compile time if you used optimizations, and you basically just pay for what you use. So because it's compiled at, because it's enabled at runtime, or you need to enable it at runtime, you use this device RTL thing to enable it. Excuse me, sorry. And then you can show an example here, lower here, using this -f OpenMP target debug, enabling it with the environment variable. And in this example, we show it has some globalization call, which might mess up on the device. I've seen this before. And if you enable this, it will enable both assertions and special information. And it'll tell you like, hey, there's a null pointer returned by malloc because your device ran out of global memory. And it helps you figure out more, what went wrong. So next slide, please. Okay, so we support many OpenMP memory allocators, and we support all of the standard ones. So the standard memory allocators are very useful for the GPUs specifically. So as we can see on this example over here, we have some like shared buffer and some flag, and you can actually use the OpenMP allocators for static allocations to specify which address space or memory type these variables should actually live in. And this is very useful for the GPU when you specifically want something to be in like shared memory or in registers or stack memory or whatever. And these are the C group and thread memory allocators. So in addition to these and some other ones, LLVM also supports some extensions to these standard memory allocators. So next, please. So these are the LLVM memory allocator extensions we support, and these basically let you allocate some types of specialized memory that certain runtimes provide. So the first one is the OMP target device memory allocation, and this is basically just standard device memory as you would get from like CUDA memmalloc or something. And that is, you can allocate it from the host and then pass it into the target device using the isDevice pointer argument. Furthermore, you have the LLVM OMP target shared memmalloc, which allocates device managed memory that is accessible from both the host and the device. So this memory lets you write something on the host and read it from the device or vice versa. We also have the LLVM target host memmalloc, which allocates host pinned memory. And what this is it's basically page locked memory that is more optimal for certain memory transfers to and from the device. And the reason that is because if the memory can't be paged out by the operating system, it's much cheaper to set up direct memory accesses. You don't need to worry about like pinning and unpinning memory for that. And these are all accessed through the standard OMP alloc and OMP free runtime calls or OMP calls. So this is just a simple example of the shared memmalloc example, or the still memmalloc allocator I mentioned previously. So we have the OMP alloc call, which just allocates a buffer of memory as you would with malloc, but we supply this LLVM OMP target shared memmalloc, which tells it to allocate this from the device managed memory. We then get a pointer to device managed memory, and we can pass it into the device using the isDevice pointer clause on the target region, which will then allow us to access it on the device. So as you can see, we are writing to it on the device, and then once the target region execution ends, we can then simply read it on the host without needing to do any explicit maps to or from the device. So this is very useful for, it's basically like unified shared memory, except for specific buffers of memory. And then we can free it as with the same call, and then we have, can return the value. Okay, next please. So in the device itself, we also support what is called dynamic shared memory, at least in CUDA parlance. So LLVM has an internal buffer, basically, of dynamic shared memory that was allocated at runtime for the GPU. If you're familiar with CUDA, you know that one of the kernel arguments in the triple chevron you can supply is the amount of dynamic shared memory. So this is basically the same concept, except you can use this runtime call that we provide on the device to get a pointer to that buffer, similarly to how you would in CUDA. The one downside to this is that it's currently only determined by an environment variable. So you need to use this libomp target shared memory size equals environment to configure how much shared memory you want to actually use. But soon we will work to improve this to where you can actually enable it per kernel like you would in CUDA. So next, please. So as Johannes mentioned previously, we support this OpenMP opt pass inside of LLVM, which does a lot of OpenMP specific interprocedural optimizations. And the way we can do this is because LLVM basically knows about the internal OpenMP API we use. We know, what certain runtime functions do. We know what their side effects are, what they'll do under certain conditions. And we can basically follow the usage of these functions to determine, certain semantic information. And we do this by, we can perform really high level optimizations such as, parallel region merging or, various GPU specific optimizations that I will mention later. And one thing we've really tried to keep on top of when we are implementing the OpenMP opt pass is to emit informative remarks and provide online documentation. And this allows users to easily locate, missed optimizations and address the issues, because in many cases, especially on the device, missed optimizations from the OpenMP OptPass indicate a significant performance hit, where you could be getting like many times better performance if you solve the issues that were preventing that optimization. So next slide, please. Okay, so this is a very high level view of what some OpenMP kernel might look like, some sufficiently complex OpenMP kernel. So we use the target teams distribute clause to basically distribute the executions of this first loop across the blocks on the device. And then we will allocate a buffer that each block will use, and then a single flag variable. Now, we will also do some single thread initialization code, but because we are inside a only target region, that will be conceptually executed by a single thread. And then we will actually do the parallel work on that big data. So this approach is perfectly fine OpenMP, but it incurs several problems when you apply this to a GPU. So for example, for GPUs typically, or almost all the time, all threads should be active during the entire region. So the standard OpenMP semantics show that this should use the fork join model, which is not very optimal on the device. So that's going to slow your program down, especially with all of these implicit barriers after the parallel for and stuff. Furthermore, you have these local variables, the buffer and L. The standard memory allocation space for OpenMP is actually like shared or global memory, whereas with CUDA, it is register or private thread private memory, and this can cause some severe performance bottlenecks when you need to start allocating global memory for something that could have been put in a register. And finally, as I mentioned before, these parallel forward calls all have implicit barriers that will be redundant, especially with a kernel, because there is no synchronization after kernel ends. So we support several optimization passes that can, at a high level, transition this idiomatic generic OpenMP code to something that is optimal for a GPU. So the first optimization I show here is this SPMDization. And what that does is basically transform this generic kernel that uses a fork join model to one where all of the threads are active from the beginning of the region, as it would be in CUDA. And we simply do this by pulling the parallel out of the inner region and moving it to the beginning. And in order to support this, we then need to manually guard all of the previous code that was executed by a single thread in the fork join model. And we simply just add a thread ID and a barrier to guard that code. The second important optimization we do is what we call deglobalization. So because I mentioned that these variables may need to be put in like shared memory space, what we can do is analyze these variables and their usage and see what memory space they should actually fit in. So for example, if we look at this buffer, we can see that it is actually shared between the threads, but because it has a statically known amount of memory, we can then just put that in a static buffer of shared memory, as you would with the shared keyword in CUDA. Now, similarly, you could do the same for the L variable, but its usage actually doesn't require sharing between any of the threads. It can simply be kept thread private. So in that case, we can then move this to the thread allocation space, which basically just means it'll be put in a register. And what we have done here is taken OpenMP's very lax description of like where variables live in memory and whatnot, and specialized it to what is optimal to its actual usage using the LLVM optimizations. And finally, we can use aligned barrier removal to then remove this redundant barrier at the end of the kernel region. And an aligned barrier is simply a barrier where it is statically known that all threads of the team will reach it at the same time. So we won't need to worry about, some threads waiting at some barriers and other threads waiting at other barriers. Okay, next slide, please. So this is some graphs we made for one of our papers to show the usage of the OpenMP OctPass, and we tested it against 4 known mini applications in HPC, so the XS bench, RS bench, SU3 bench, and mini QMC mini apps. So as you can see with our base on the left, we used LLVM 12 as the base. We achieved more, reasonably better performance using this OpenMP opt pass with all of the optimizations I just mentioned on these real-world OpenMP offloading applications. So on the far right of these graphs, where applicable, we have the equivalent performance for the CUDA version. And you can see in many cases, we begin closing the gap between the OpenMP and CUDA versions of these mini apps simply by applying our OpenMP optimizations. So next slide, please. So another thing we did was redesign the OpenMP device runtime with these OpenMP optimizations in mind. And so this allowed us to basically target what we know the new OpenMP opt pass can do for the GPU. And you can see here that with this new runtime, we basically closed the gap that you previously saw for XS Bench and further reduced it for some of these other applications we tested. So basically, the combination of this specially designed device runtime and this OpenMP optimization pass allows us to take the very, very broad definitions that the OpenMP standard sets forth for GPUs and then specialize it to something that is competitive on the GPU despite being much more complicated. So next slide, please. Okay, so I mentioned remarks previously, so I just want to go over some of the general usage of remarks in LLVM because it can be very useful if you know where to look. So LLVM has support for several basic optimization remarks. So this is -rpass, which is simply to report on any successful optimization. So this is good to check if something you expected to happen actually happened. We have rpass analysis, which will typically provide some extra information on why or why not a certain optimization was or wasn't done. So this one is typically used if you're trying to identify why a certain optimization that you expected to happen didn't. And then rpass missed is simply to indicate if an optimization failed or it wasn't applied because it was deemed too expensive. So this is very useful for identifying missed transformations in your application. So ones that are particularly useful is, as mentioned before, we have our missed OpenMP opt runtime remarks, and we also have the loop vectorize remarks. And the loop vectorize remarks are very useful for, vectorization heavy codes, something that might be run on like Fugaku, for example. One more thing we do for OpenMP opt specifically is to provide an identifier that can be looked up easily in the online documentation. So every single OpenMP opt remark will typically have some little keyword after it, like for example, OMP100. And that will let you just Google that or look it up in the documentation. And there will be a description of why or why not that happened and, potential ways to address it. So next slide, please. So just want to mention real quick, one handy thing you can do with remarks is also utilize profile guided optimization. So for large applications, just enabling remarks can become very noisy. And that can kind of drown out all of the code you're actually interested in. So like a regular large application could provide like 5,000 missed remarks for like vectorization. And that will only apply to like these loops that no one cares about that couldn't be vectorized anyway. And one way you can kind of get around this is using profile guided optimization. So here's an example of how you would generate the profile instructions. And basically what that does is builds your application with code inserted that will be called while it's running to measure performance about like run times, how many times it's been reached, for example. And then when you run your application, it will write the results of that performance profiling to this file. So once you build your application and run it, you'll have a bunch of these profiling outputs that you then use the LLVM prof data tool to merge them all into a single profile data. And then you can reuse this as long as you think it's relevant. So once you have this profile data, what it allows you to do is only show remarks for the hot code paths. So you can use the -f profile instruction use, which is the one we previously merged, and then use these two show hotness and hotness threshold instructions. And that will basically let you say, I want to know how hot or expensive this function was to compute, and I only care about remarks for like missed passes that were above this threshold. And that basically allows you to take this large program and kind of get a sorted list of all of the hot code paths that missed some optimization you're interested in. So this is a very quick way that you can get similar results to larger performance suites, kind of like LLVM, like Intel vTune. This is very useful for certain things like vectorization. So this is just an example of the LLVM remarks to kind of show why this is useful. So first off, on the left here, we have this simple reduction loop. But if you actually look at this with the RPass analysis, it'll say that it didn't vectorize that loop because it can't prove it's safe to reorder floating point operations. And this is very common because the IEEE standard dictates that you can't reorder floating point operations because they're not associative. But you can see that this loop wasn't vectorized that maybe you expected it to be vectorized, and then take the appropriate action to make sure that the transformation you want to happen actually occurs. And furthermore, for OpenMP opt, you can see that we have this random function on the device, and it has some globalization that I mentioned previously, which is where we had to take this local variable and put it in global memory. So whereas this variable should be in thread private memory, because we have a call to a function that we can't analyze, we just assume that we can't do that deglobalization optimization I mentioned previously. But if you enable the RPass analysis, it will give you a warning on this saying that it couldn't do this transformation, and it will tell you to use the no escape attribute, and then you can do that and solve the problem. So next slide, please. Okay, so finally, this is a real quick one. We're working on a device math library for the GPUs. So currently the compiler kind of eagerly translates math routines to their vendor-specific versions. So for example, if you had a sine call in your program, the front end at pre-processing would basically just turn that into a NV sine call. And this works, but it has the downside that LLVM knows how to optimize the sine call, but it doesn't know how to optimize the NV sine call. And furthermore, this makes it more difficult to create more generic offloading code that you might want to utilize if you're doing something like JIT, where you want to like retarget things or target things dynamically. So the solution is to link these definitions late by just defining a device math library that, instead of doing it early, where we replace these sine calls eagerly, we do it late at link time using the new linker wrapper that I mentioned. So next, please. Okay, so this is just real quick to mention these. These are very useful flags if you're having some problems with performance. So the -f OpenMP CUDA mode flag basically asserts that globalization does not happen. So what I mentioned previously, where you have like the OpenMP runtime allocates something in global memory, or where we had that application occur. Sorry, my computer turned off from idling. Then that will basically statically assert that we don't have data sharing. It's like CUDA, where everything is thread private. And that is very useful for some applications. So I would recommend, if you tried LLVM for like one of your large applications and you had like a resource exhaustion or is extremely slow, the problem is almost always due to this globalization. So I would encourage you to first enable remarks to see if this is your problem. There should be a missed remark for it. And if you can't deal with it in code, just use this -f OpenMP CUDA mode, and it might solve your problem. It might also break your program, but it's worth a shot. So additionally, we have this -f OpenMP assume no thread state. This just statically asserts there's no per thread state, such as if you were using nested parallelism or like tasks or something. And this can improve the performance of almost every application. I haven't seen many that made use of this per thread state that we need to support in order to be standards compliant. But you can do this and it should improve your performance by a reasonable amount. And hopefully in the future, we will improve optimizations where these two are no longer necessary. But if you're having problems wrangling with the compiler and you want better performance, you can try to statically assert these things. So thank you. I will hand it over to Sheila now.
All right. Thank you, Joseph. Hi there. I'm Shirley. I'm a PhD student at Stony Brook University, supervised by Dr. Barbara Chapman. In the next few minutes, I'm going to talk about some works I have been working on. So the first one is about the just-in-time compilation. So currently, LLVM OpenMP features ahead-of-time compilation. As Joseph had shown before, and some command line here, we have to specify the offloading target as well as the SARP architecture when compiling OpenMP programs. So, for example, if you are using a NVIDIA A100, so you have to specify -f OpenMP targets, VPTX64, and SM80, and for same thing for AMD GPUs as well. One of the reasons we have to specify that is the binaries for different sub-architectures are not compatible. So this figure shows how things work for NVIDIA GPUs. So at compile time, in the second compilation path, the device compilation path, we have the device code, and then we have the device assembly. Then for NVIDIA, we call PTXAS and call NVLinks, and then embed the device image into the host object to get a fat binary. And at runtime, during the runtime initialization, we call a CUDA module load data to basically load the device image into the target into the GPU, and then we launch the at kernel launch. We launch the corresponding kernel. So just JIT compilation is not a new concept. Many heterogeneous programming models have already supported JIT compilation. For example, OpenCL and the SQL, they support that by nature. And CUDA actually also supports JIT compilation in some sense. They basically call the PTXAS at runtime. So at compile time, they just embed the PTX into the binary. In addition to the portability, performance is also another aspect to use JIT compilation, because during the runtime, we have more information, and those information kind of only available at runtime. So in this work, we bring JIT to LLVM OpenMP. Here is an overview of how we implement the JIT support in the LLVM OpenMP. So with all the changes developed by Joseph, as he mentioned before, now we can embed the bit code into the fat binary, into the application. And at runtime, we do nothing at runtime initialization. At each kernel launch, we first create a buffer, create a LTO module from the bit code. We are using LTO module in LLVM because it has very good middle-end optimization pipeline, and also the backend, so we don't have to re-implement everything backend and the optimization pipeline again. And we also there is also another reason we use LTO module, but I'm going to talk about that later. So after we create that from buffer, we have an LTO module, and when we create that, we have some runtime information for and also some device information, like what the sub-target the device is, and so on. And then we call the LTO code generator to generate the assembly. And actually, for CUDA, for CUDA or NVIDIA device, we can directly feed the assembly to CUDA runtime, because they support the, like I told before, they support the JIT compilation in some sense. But for AMD GPU, we call all of the tool chains as well. So yeah, once we get the device image, we load that image to the device, and we also buffer those modules for later reuse, and then we launch the kernel. So all of those things happen at the kernel launch, which means this kind of JIT only applies for that kernel launch. So those runtime information include kernel arguments, how many threads in the team, and how many teams we are going to use. And it also has compute capability of the device and the number of registers, such that we can tell the underlying JIT that okay, we can actually use more registers than the assumed one, which could give us a better performance. Here are some details. We introduced some optimization into that because we now have some information that's only available during the runtime, right? So the first one is specialization. Now we have the kernel arguments like the value, the pointer. So we have scalar argument specialization, basically just to replace all of the scalar kernel arguments to specialize it. It can help us to determine many stuff like the loop boundaries and such that we can further optimize out some loops. And for pointer arguments, there is no point to specialize it because during at different run, the pointer can be different, right? So there is information that is very important, which is alignment, because compiler has an assumed number. But usually it is more. We have a better alignment at runtime. We can know that. So we just replace all of the pointer alignments, and potentially it can get us better vectorization. And we also know how many threads and how many teams we are going to have. So we fold all those runtime function calls in the code such that it can also give us some better performance. We also have some internalization, basically to internalize all feasible global variables and can help us optimize more code. So here we only keep symbols related to current kernel launch. So for those functions for another kernel launch, or another kernel, they are optimized out. These can help us to keep the device image as small as possible. But we have so many specialization, but it only valid, it's kind of only valid for that kernel launch, right? But what if in another kernel launch we have the same arguments or compatible arguments? We don't want to JIT every time we launch the kernel because we can launch a kernel for so many thousands of times at each one. So that's why we have a multi-level caching. The first level is target table caching. Target table is a table contains all the host entries. Host entries can be global variables and kernel entries, and their corresponding device addresses. And then every time we have a kernel launch, we first check whether we have the target table. Basically means whether we already have the corresponding device image loaded to the device. If that is the case, we can directly use that device image, use that target table. We check whether it is compatible or all the cached target table is compatible with current kernel launch. How to define the compatible? I'm going to cover it later. But if the target table cache misses, we come to next level caching. It is the device image caching, because at each program run, we have JIT the device image, and at the end of the program, we store all the generated device image into a file. Then in the next run, we load all those images from the file and to store it. And when we have a kernel launch and when we have a target table cache missing, then we look up the device image caching to see if there is a device image already good enough for us to use. Then we load it to the device, and we have the target table. And now we also cache the target table for next kernel launch. And during the whole process, we have to interact with LLVM context and LTO module and so on, because LLVM is not a thread-safe architecture. So we have to make sure that everything here is thread-safe. So we cache the LLVM context and the LLVM module. We also extend the LTO module to make it support clone. So next time we only use LTO module clone instead of create from buffer, because that can give us some better performance and to save some host side overhead. So because our specialization is per kernel launch, and we already have those cache, that's good. But what if for same kernel entry, but in different kernel launch, there are always some, oh, sorry, before I talk about that, let me first talk about how can we say whether a kernel is compatible with current run. So we introduced a concept called the kernel identifier. The kernel identifier includes the kernel name and target device, including the sub architecture, and all of those actions applied to the kernel, which those optimization, specialization apply to the kernel. So all the for those scalar values, if the values are identical, then the two kernel is compatible. But for a pointer argument, for pointer alignment, if they have if P and A is the alignment, P is the value of the pointer equals to a Q, and the alignment, it is compatible. So here is an example. We have the two addresses. The values are different, but they kind of compatible because they all align to 16. So like I said before, now we have everything. We can check whether it is compatible. But what if there are some kernel arguments always different in kernel launch? Because we have an example here, the PEP in spec Excel benchmark. It has just one scalar argument. It has about 16 arguments, but just one scalar argument varies in every kernel launch. So if we just specialize for every kernel launch, it's going to have about 2,000 different just specialized kernel images, which have a huge host side overhead. So the performance is really, really bad. So in order to deal with that, we add the specialization statistics. So a specialization statistic is set up for each kernel entry. So every time we specialize the kernel, we record, okay, we specialize for this value, and for that kernel argument, we specialize for that kernel argument, and the times or how many times we specialize that, the count for that. And if the specialization ratio of 1 point is greater than a predefined threshold, then we skip that specialization. Next time we have that, then we can use the more generalized version. And this saves us a lot of huge host side overhead, and we can see the performance improvement later. So using JIT, another benefit of using JIT is the sub-target portability. So now we can compile once and run anywhere for the same vendor, because currently we only support the same vendor sub-target portability. So now we don't have to specify the compute capability for NVIDIA GPUs or the ARC, the GFX version for AMD GPU now. Now let's just look at some preliminary results. This is the end-to-end execution time speed up. So this bar stands for the ahead of time compilation, so it's all 1. And the JIT version for post-stencil, it can give us more than 3 times performance improvement, and also we can observe the similar trends for another benchmarks. And the JIT cache means we apply the offline caching such that we can just use the device image in next run. And as we can see here, it gives us some kind of performance improvement in different situations. That is the end-to-end execution time. But for kernel execution time, because now we optimize the kernel with the runtime information, right? So for different benchmarks, we can see we all have the performance improvement. And oh, by the way, for the PIP, as we mentioned before, right? If we don't have the specialization statistics, the speed up will be like 500 or 500 slower. But with all those statistics, with the specialization statistics, it can have the same performance as ahead of time compilation. And even for the cached version, we have a slightly better performance. In the future, we are going to have the real portability. We no more just compile once and run anywhere for the same vendor. We can just compile it once and run for any vendor for any architecture. So instead, in the front end, the generic IR will be emitted instead of the target dependent LLVM IR. And with all the device math library, Joseph has mentioned before, we will link all those target dependent libraries at G time, so device runtime math libraries, and then generate the target IR accordingly and to go through all the pipeline layer. The next topic is about a virtual GPU. It's actually collaborated with the Antman Petal. The motivation is, so we already know parallel programming is very challenging. It's very challenging, and programming accelerator is actually more challenging because it's more complicated. The architectures are totally different. One of the reasons is it is actually lack of mature tooling that can be used to inspect a program, because nobody can make sure that they don't have to debug their code. For now, the gold standard for debugging is still all those host execution, because on the host we have a pretty bunch of mature tooling options. So in order for a better development, why not just emulate a GPU environment on the host such that we can hook up all those device toolchains, the debugging toolchains, using all the debugging tools. Before we talk about our implementation details, let's take a brief look at the compiler and runtime support for LLVM OpenMP. So, say we have a source file, and the compilation actually has two passes. The first pass is the host compilation. It has a host. It recognizes all the host, generates all the host code, and also recognize target regions and make preparation for the second compilation pass. Actually, the device compilation pass. The device compiler can generate the code that can run on the target, on the GPU. And as part of that, a device runtime library is linked into the user's code. And once we get the device image, it is embedded into the host object and to get the fat binary. And at runtime, the program depends on libomp and libomp target, and we have the plugins, and those plugins is directly call those vendor SDKs. So in order to support all of those stuff on the host, we have to make sure that first our device compiler can compile the code, to generate the code for the host, which is already there, right? And we have to make the device runtime support the host as well. And on the right hand side, we have to make a plugin that can support all of the execution and the execution environments on the host as well. But we don't have the vendor SDK. So the first one is about the compiler support. So how can we compile the program now? We introduce a vendor called the OpenMP vGPU. So now we just have to call the -f OpenMP targets, and this arc corresponds to the host architecture and -OpenMP vGPU. The reason we just add a new vendor because it can give us the minimum code changes in the front end actually, and it doesn't break the function between the front end, middle, and the back end. And for example, now if we want our program run on x86 architecture, then we just need to say x86 OpenMP vGPU, and the same thing applies to ARC64. Another stuff we have to as a supporting compiler is a GPU memory hierarchy actually contains more levels compared to CPU memory. One of the stuff is shared memory. So actually in the device runtime or even in the user's code, they may use a shared variable. So shared variable is only visible in the thread block, right? So in order to support that, we just make an array. The M here stands for the maximum number of thread blocks we are going to support. So every use of the shared variable is replaced with a function call to get the corresponding block ID and then to access the corresponding array element. This is implemented in middle end. So device runtime is the one we have to take care. So thanks to our previous work to write the LLVM OpenMP device runtime in OpenMP, now we can just compile the to use the OpenMP compiler to compile the device runtime. That was impossible before because previous the device runtime was written in CUDA and heap, and it cannot be compiled for host execution, obviously. And we definitely have some target-dependent functions. For those functions, they are implemented accordingly inside of declare variant regions. And as you can see here, we implement this function and to tell, okay, if the device can the CPU, then this function is generated. And target, we in CUDA for CUDA or AMD GPU, we have some target-specific intrinsics, but for our host execution, they are emulated via some per thread environment object, which are provided in the plugin for which I'm going to talk about now. So in the plugin, we have the runtime environment. We have thread pool. And all the threads in the thread pool are organized into three hierarchies: thread, warp, and CTA, which basically same as a real GPU. And all the synchronization done through a CPP20, the STD barrier, because the GPU, we have different levels of synchronization. And yeah, they are implemented in that way. For now, we only support the simplest scheduling policy, but we are going to add more in the future. There is an instruction, shuffle instruction, which is not available on the host. So we implement that via some buffer, and we use those buffer to emulate those register for the shuffle instruction. As for how many threads for per warp and how many warps per CTA, they can be configured at runtime. And as those figures, the figure shows here, those threads are organized into different hierarchies. Here are some use cases. So this figure shows we are using the debugger, and we encounter a segmentation fault in our target region. And because we have the reference null pointer, and here we can also set some breakpoints, and then we can stop here, stop at the corresponding point. And we can also use those fine-grained or memory sanitizer, and this figure shows the fine-grained results of the execution. The next one is actually, it is the last one, is about the OpenMP device info. It was developed by Jose from Oregon National Lab. So it is actually a command line utility by using LLVM target and the corresponding device plugins that can list all of those device information seen from OpenMP runtime. All the vendors, of course, their SDKs provide a similar tool, but here we just use that one binary that can support all of the vendors as long as the corresponding function implemented. So this on the right-hand side, we show the example of run on my workstation. So for those devices, if their corresponding functions are not implemented, then just print a function not implemented. For NVIDIA device, we already implement that function, so we can we can see a huge bunch of information is shown here, which are really helpful. For now, we only support VIA GPUs. We are going to support more in the future. That's it from my side. I'm going to hand over to Michael. Thanks.
Thank you, Chile. I'm talking about the OpenMP 5.1 editions of loop transformations, specifically about its implementation and claim. So first one of the motivations you may have seen, like this vendor extensions to add unrolling. Most compilers support these, but these are all use different syntaxes. For instance, GCC added an unroll pragma in GCC 8, I think. But they insist of using a GCC namespace in the pragma, so you would have, for instance, use preprocessor macros to be vendor neutral in your compiler. So we in OpenMP we added it to a standard which all of these compiler intend to implement eventually. So we don't have the need of vendor specific extensions for this anymore. Next slide, please. So the first, let me tell you about the unroll pragma. So unroll supports multiple modes, the simplest of which is just full unrolling, where you need a constant trip count in order to be able to do it, and it just replaces the body code with the number of instances with the instances. Next slide, please. The second mode is partial unrolling, where the number of trip counts of the loop is not needed to be known, but we're going to have a kind of remainder loop to execute the instances which are not multiple of the unroll factor. And next slide, please. The third mode is then heuristic unrolling, where the compiler decides how often to unroll. Most compilers have a heuristic to determine what the best unroll factor is, usually with the intent to not exceed the L1 instruction cache, and we can make use of it, tell the compiler explicitly to unroll this loop. Next slide, please. In addition to unrolling, we also added a tile construct to OpenMP, which saves you some. So tiling is often an often used loop optimization for speed, but the actual code for using it can get quite complicated, and as you see on the right. This one shows just having the complete tiles, but if you have, next slide, please. If you have loops which where the loop iterations are not the multiple of the tile size, it gets even more complicated. In OpenMP, we added the possibility that the compiler is allowed to semantically allowed to put these special cases in some extra code in order to not impede the compiler from optimizing the main code, especially when the partial tiles usually do not exist. You often choose tile sizes which are or loop iterations, problem sizes which are a multiple of the tile sizes. So in this way, this does not impede the optimization of the code. Sorry. Although this hasn't been implemented yet, it's planned for the future. Next slide, please. You can draw comparisons if you use chunking. For instance, if the work sharing loop 4, you specify a chunk size, a static with a static chunk size. An example on the right, it's 4 to decrease the overhead you have per thread here. If you have multiple loops and you have the collapse 2, you get chunk sizes or chunk shapes which do not logically correspond to the to the actually code. So if you use sizes instead, you see on the left, you get some code which corresponds more to the logical shape of your problem, specifically for stencils. Next slide, please. Here's an example we're showing what the effect of this is. And this is just doing some manual optimization, playing around with the tile sizes. I'm also working on a solution that for auto-tuning that automatically determines these tile sizes, but this is just for illustration. You can easily play around with the tile sizes. In this case, on an NVIDIA GPU, where just by tiling, you can easily get a speed of 3. If you choose a tile size too large, you have the problem that you don't have enough parallelism to distribute all over the GPU. So in this case, the performance skyrockets. So you need something like a sweet spot, which in this case is a tile size of 5 times 5 times 8. I choose the innermost tile size always constant 8 to not impede with vectorization, respectively SIMT vectorization. Next slide, please. So this is just the slide, the only slide I talk about the implementation. The details might not be interesting. I actually have 2 implementations. One works on the abstract syntax tree level, here highlighted the SEMA level, highlighted in red, which does this kind of transformation on the internal representation of the syntax tree. The other this is the one which is the default now. I also have an implementation in the OpenMP IR builder, which is also used by Flang. So you lower it from MLIR down to LLVM IR, which is then intended to be used by Flang, but it's also just as possible to be used by any front-end DSL or whatever that uses the OpenMP dialect and can implement this tiling. Next slide, please. So as I said, the main default implementation on the SD level has been implemented and released as part of Clang 13. Since it's an upstream, I also hope that other vendors which base their compilers on Clang will pick it up and support it eventually as well. The other implementation, the OpenMP IR builder, is to be used by Flang. There is not support for it yet from the FEAR level, from the Flang IR level yet, so it cannot be practically used at the moment. I also know from the GCC folks they are also working on an implementation, but has not been upstream to any release version of GCC yet. Next slide, please. So for the future, I hope we are adding more transformations, not just tiling and unrolling, but also things like loop interchange, loop fusion, etc. And also be able to combine multiple transformations on a single loop in various ways. So at the moment, this is possible, but just to the outermost loop of the generator loops. And as illustrated on the right, there's going to be an apply clause, which allows you to apply more transformations, or a loop directive like Pragma OMP parallel 4 on any loop as well. So this is planned for OpenMP 6.0. Which is scheduled to be released in about 2 years. Thank you. Next slide, please. So I'm giving further the talk to Johannes then.
Great, thank you. So we're going full circle here. I'm going to present the last few topics, and then we're opening up for questions. Hopefully people still have questions after they put all of them in the comments. The next thing we're looking at is remote offloading. So if we go to the next slide, The idea is that you're actually currently, if you use OpenMP and you use OpenMP offloading, you're somewhat limited to your GPUs in your node. There's only that many GPUs you can put into a node, right? And if you want to use more than that, you're bound to introduce a second programming model, which is not necessarily what you might want. You might want to use one programming model because you only need, let's say, 11 GPUs in total, 12. So adding MPI for that is a huge investment. And if you don't have a local GPU, but you kind of want to do local development and local execution for some reason, you might want to employ GPUs that are in the cloud, in a cluster, or somewhere else. And with remote OpenMP offloading, you can do that. LLVM 12 and further supports it. We actually have two different backends to do so. One is through the Google remote procedure calls, and the other one is UCX. And what we've measured is that depending on how you set it up, you actually get fairly nice scaling behavior. So what we did is we modified XSbench proxy app to use multiple GPUs. And then we exposed remote GPUs on a HPC cluster as if they were local. So from the perspective of the programmer, there was no distinction particularly. And then we really scaled it up to, in this plot, 72 remote GPUs. I think in like our latest evaluation was up to 120 GPUs on which we run this. And each execution of the XSbench main computation kernel, including data transfers, was at the end of the day 2 times as, it took twice as long as if you only used native GPUs. So there is obviously an overhead involved, but even on this very simple scheme that we had with a star topology, we were able to effectively utilize a lot of a HPC cluster just using the OpenMP programming model. There's like key things that we discovered that OpenMP has to address to help you with distributed computing. But future will tell if that is going to be something useful. For now, the OpenMP remote offloading can also be used to do same node offloading. So you basically offload onto a new process on your actual node. You would do that because that way you can discover memory mapping errors, even if you use the host. So you offload into a new process on the host, and if you forgot to update a pointer or map some memory, you will actually see the same segfault happening on the host that would happen on the device. The difference is that you can now use host tooling to determine where it happened and why it happened, which oftentimes is way more stable and mature than device tooling. So that is kind of, on the debugging side, remote OpenMP offloading is really useful for people, even if they don't want to actually use hardware that is in the cloud or in a distributed system. And the next thing, we go further. Yeah, the next thing I want to talk about a little bit is profiling support now and soon. So since LLVM 12, we actually have simple profiling support as part of the OpenMP offloading runtime. And if we click on the slide here, just unfold everything. So if you build LLVM with offloading support enabled, you can just set an environment variable to get a JSON file that uses the Chrome tracing format and source information to tell you where your time is spent. So you can use Chrome to create a trace of your program with summaries about all the function calls. And you can use other tools that are available, that understand the Chrome tracing format to analyze your program in more depth. And this is unrelated of what target you're offloading to. So this works unrelated to OMT and other OpenMP specific tooling things. And it's really lightweight. There's documentation online if you want to know more. And we're currently working on an addition to this host profiling. We go next slide, which is kernel profiling. It kind of works, but it's not upstream, and it's we're kind of still have to figure out a couple of things. But the idea is that you enable it at compile time, and it will tell you how you execute your program, how you execute your offloading kernels, your offloading regions, what kind of modes you execute them, how often, what features of the OpenMP runtime you're using. And based on this profiling, we can then recommend you options that you can use to specialize your runtime and thereby pay less overhead. So a specialized, more lean runtime will mean that we either don't have to pay for it at runtime because the features are removed at compile time already, or you just get faster compile time because even if we were able to remove the features, we don't have to invest the time. So the workflow will be you run it with kernel profiling, you compile it with kernel profiling, you run it, and then you get suggestions on what compile time flags and or kernel annotations you're going to use to only to get kind of a custom runtime implementation for your particular file or actual kernel that gives you all the features you need without any overhead of the things that you don't. And this is kind of important because OpenMP comes with a lot of features. Basically, almost the entire host OpenMP features are technically available on the device. But if you, people don't use them, and if people start using them, it's going to be slow, at least some of them. In this way, we can help the compiler to reduce your overhead by eliminating them statically, by promising not to use them. And in order for you to understand what you're using and also understand performance behavior, we're putting this profiling information in, and there will be more in future, and that's coming soon. Now, finally, I want to give a little overview of what the vision looks. So where are we heading with all this? I mean, you've seen all these features that we're adding to OpenMP, and you've seen how it's compiled and optimized in ways that don't exist yet for any other parallel offloading language. And this is roughly the picture that denotes the compilation pipeline for LLVM OpenMP right now. You have OpenMP code, you pipe it into Clang or Flang. That is then translated to LLVM intermediate representation and OpenMP runtime calls. And then we perform OpenMP aware optimizations on that. We link in the OpenMP runtimes, and then we execute this on CPUs, GPUs. We have profiler hooks, debugger hooks, remote offloading, virtual GPUs to do debugging, just-in-time compilation. There is FPGA targets, not in LLVM upstream, but available online, and so on and so on and so on. So all these features are kind of available to you if you use this compilation toolchain and these runtimes. Now, what we really want to have is we want to allow people to use their particular favorite programming language, because there is little reason that people couldn't use OpenMP and CUDA and HIP and SYCL all in the same application. They can be made interoperable, and they can actually be made interoperable and fast if we agree on the way we compile them. And what you see here is work in progress plus research prototypes plus a few things that haven't been started yet that give you an idea that all these languages on the left, everything, CUDA, OpenACC, certain DSLs, Chapel and Julia, they all can go through Clang, Flang, or MLIR to target the same LLVM IR plus OpenMP runtime calls. So the box in the middle is shared across all these languages and all these backends. That gives you the ability to use any language on the left in combination with another language on the left, and then actually compile that to any CPU and GPU that is supported by OpenMP, use the hooks, the remote targets, JITs, everything. Like all the features become available to you, no matter where you start on the left. And everything becomes interoperable at some point. And we already shown that the CUDA and OpenMP interoperability works. We actually have prototypes to do far more than that. So if you have CUDA code, you might actually not need to rewrite everything. So this is kind of really the vision that we're having, where we're going, such that all these investments we made in the OpenMP optimization, in the backend parts, the plugins, the runtimes, all these features, that can be used even if you don't have OpenMP pragmas in your code, because the pragmas are just the first level of syntax. They're not necessarily what you need to utilize OpenMP at all. I think that was our entire presentation. Yeah. So this opens up the floor for questions, and I would suggest people, like assuming it works out, people just unmute themselves and start to ask questions. Feel free to address them to someone explicitly or mention the part that you're interested in, and then we'll see how that goes.
Maybe just a quick general question. Do you have any updates on flying by any chance?
Yes, partially. So we have the flying development has moved completely to LLVM upstream. LLVM upstream is able to compile flying codes. It has the necessary driver and code generation patches to compile the first Fortran codes. The OpenMPs that we successfully, in kind of a prototype run, recently compiled Fortran with host OpenMP to run in parallel. So that works on the prototype stage. And now we have to hook up the rest of OpenMP, especially the target offloading parts. At the same time, a lot of people are working to add the newer Fortran features and stabilize things. So we're looking much better than we did recently, especially now that the entire development has moved to LLVM upstream, where we're hoping that actually also improves our turnaround time in getting things done.
Okay, thanks.
People should feel free to ask more questions.
So Johannes, I had a question for the remote offloading. So how would you imagine how the data transfers between the GPUs on different nodes would work under the hood? Would there basically would OpenMP have to implement similar things like OpenMP, like MPI, to get good usage of them, and all the tricks they have to do?
Yes, kind of. So right now, I don't think we actually implemented the device-to-device memory transfers, but we could have. So we only, like, we have this host-centric model, we kept that, and we only did implement the host-to-device offloading, like memory transfers. So device-to-device from one remote device to another is something that has to be done. But even the host-to-device ones, basically what we do is, if you have a map, the plugin decides how to move memory from the source to the target. That could be a CUDA memcopy or an HSA memcopy. And if you use the remote offloading plugin, it basically does either a Google Remote Procedure Call memcopy, or it does a UCX memcopy from the source to the target. And then on the target, it will basically daisy chain the next plugin. So it will say, okay, now I moved the memory. Now I will call the plugin that is responsible for the accelerator on the remote system to handle the rest of the way. So the remote offloading plugin is kind of daisy chained with the existing ones. It handles the memory transfers across nodes, and then the other existing plugins do the last step from the host on the remote to whatever accelerator there is on the remote. Does that help?
And when would it also be possible to split in a single allocation between multiple remote GPUs, or?
Yes. So for our evaluation, we actually implemented that kind of transport optimization where, because our remote nodes had 8 GPUs each, and then we implemented into the runtime some recognition that if you move data to a remote device that already is on the remote host, you can skip the copy, wait for, like, make sure that it's actually already there, so do the direct securitization, and then utilize the memory that is on the remote host right away in certain situations. So we kind of played with this. It's certainly not like as good as you want it to be and all the features in there, but that is absolutely possible, and that helped us to scale onto the 120 GPUs reasonably.
Mm-hmm.
Okay. Doesn't seem that there are more questions. I'll wait for another minute.
Yeah, this is Jean-Luc Fatper at ORNL. I have a question about the debugger. It looks like it's nice. Now you can see a lot inside your kernel. So can you, if you have several, for example, several pointers and one is null, does it tell you which one it is, or does it give you these kind of details?
So we had the debugger stuff in a multiple of these projects. Like, the one thing you can do now is you can use the virtual GPU as an offload target, which is not like host offloading, but it actually does the compilation and the offloading runtime parts and so on, like it would for the GPU. And if you then use that offloading target, you can attach to GDB just regularly. And then you can see, I mean, with debug information, you can see the values of all the pointers. You can set the breakpoints, do regular debugging as you would on the host otherwise.
Is it functional on the ECP machine, the Summit and Crusher?
That's a good question. No, it is not. Okay. But we can make that happen, and feel free to ping me so I don't forget.
Okay, thanks.
Yeah, and for the info flag, it won't tell you which pointer caused the seg fault on the device. If it's just regular device debugging and error messages, it'll just say that it happened.
Okay.
Are there any plans to allow target regions to offload or to be split to multiple devices? Let's say of the same type.
Yeah, that's a good question. I mean, I don't have immediate plans, and it's a little tricky to do that while completely adhering to the OpenMP spec. The next thing I was hoping to look at, the next bigger thing, is do something like a device auto, where you can just say, okay, I don't like find a good device for this and move it there. as part of this, we might be able to do some splitting, but we probably will have to require the user to give us certain promises about target regions and so on and so forth, because splitting a target region with in all its generality, I kind of doubt that we get that.
So I would, this is Vivek, I'll just say that yes, there is some work to do to split the split or partition that target region across multiple devices, actually for OpenMP 6.0 that I'm involved with. The difficulty I think here is managing the dependencies, the data dependencies when you partition that, let's say the loop across devices. So you offload some computation, but that computation has to respect data dependencies. So the mapping has to be done in such a way that data dependencies are respected. And that requires some thinking. So I don't actually, I will say I don't doubt that this can be done. It is hard though.
So what about if you just limit it to, if you go from multiple device just to NUMA programming, let's say on the CPU and you have 2 sockets and so on, what about you do the partitioning across NUMA domains and the user defines, okay, I want to run this problem of my target region on NUMA domain 0, another problem on the other NUMA domain, something like that. Is that something that you are working on?
That's part of, yeah, that I mean, are you saying across a CPU, like a NUMA domain and a GPU, or are you saying like just across 2 NUMA, like CPU?
I mean, if you have NUMA domains, for example, on the CPU,
Mm-hmm.
right now, if you want to program that as in a single parallel region, you have to know about first touch policy, you have to initialize the data in parallel. There are a lot of unknowns that the user probably doesn't know about. So if the OpenMP can specify something like that, like NUMA allocators and NUMA scaling policies like that, that wouldn't open it up to be actually usable as a single CPU instead of 2 sockets.
Right. Yeah, that is something that might be an easier thing. I've just been looking at multiple devices, but that could be a direction that might be easier. Yeah.
Mm-hmm.
Look into it.
And do you think that would be part of the tiling?
I think.
Where would you put it?
Tiling is kind of orthogonal to.
Okay.
I mean, not. It's related, but it's just. Tiling.
So I was thinking you tile your problem and then you specify where the tile, the affinity of the tiles to NUMA domain, something like that.
Right. The affinity of the tiles would be could be specified that way. Yeah. Yes. That way. Yeah, we could. We could have like a NUMA affinity of the tiles to a NUMA domain, and maybe there's some way we can specify that. But I think, yeah, it's a schedule. I mean, yeah, I don't want to mix the scheduling of work with the with the partitioning of work within scheduling of work to a processing element, to partitioning computation and data within one processing element. It's that right now, actually, we're very clear in OpenMP, the direction OpenMP is going to make that those 2 pieces distinct. Michael Cruz, if you want to say something more.
Yeah, I agree with Rick. It's kind of orthogonal. You can combine it. You can like choose the tile size beforehand, and then then you have like logical units of work, like what we call the logical iteration space, that one can decide to schedule with on GPU, CPU, threads, etc. So even like, for instance, virtual GPUs, if you like. So, but we are working on, yeah, Vivek works on multiple GPU support.
Yeah.
Okay, thanks.
So I had a question about multi-GPU support, since we are discussing. So all that is needed, I think, you know, in the for making use of dense GPU nodes is like, I would say, a wrapper over CUDA peer-to-peer access functions. If something like that exists, then it would be instantly helpful.
Exactly.
So
yeah, go ahead.
For the record, on a single node with multiple NVIDIA GPUs, you can just do, there is an OpenMP device-to-device memory transfer API already.
Oh, I see. Okay.
For NVIDIA GPUs. So if you have a single node, 6 NVIDIA GPUs, you can move the memory from one to the other, assuming the CUDA drivers for that system allow you that.
That's cool.
And
thanks.
Sheila, does that work for AMD?
For now, no. AMD doesn't implement that.
Yeah, well, we'll get there eventually.
Yeah.
I guess actually this is something, I mean, if we could have something like a target update where you can specify the device ID, that's, I mean, yeah, that would be interesting.
We have that. That's what I said.
Okay.
So we have a question in the chat from Chris. Joseph, can you answer that? Second.
So that is it possible to create a single executable supporting offloading to NVIDIA and AMD GPUs? So I'm assuming you mean like one program that if you execute, it will run on an NVIDIA GPU if that one exists, or an AMD GPU if one exists.
Yes, that's correct. Yeah.
I think that will happen. I've never tested it. I'm doing more work to improve that. But I think what will happen right now is, as long as you have the like software kits necessary to create those images, the OpenMP runtime will basically iterate through every single embedded device image and just check if it works with a given device. So it'll pretty much just use the first device that it finds. So if you have a binary that has a valid image for both CUDA and AMD, or NVIDIA and AMD, and you run that on a system that supports AMD, it will look through that and say, oh, that's an NVIDIA image, I don't support that, and throw it away. And they'll say, oh, there's an AMD image, I support that, I'm going to use that. There's more work going towards that front to make it more intelligent, but I think it'll work, but I haven't tried it.
Yeah, what Joseph is working on right now is really to have multiple sub-architectures supported, so you can, you know, embed specializations for all the different AMD GPUs, as an example.
Mm-hmm. Yeah, and there's also some work going on in the runtime itself to embed some additional information to let us more intelligently choose, like, oh, this is an image for a SM70 NVIDIA GPU, but I'm an SM80, so I'll use this other image instead. Stuff like that.
We still have a few minutes. If people have any questions, comments, concerns, it's a great time to get them out there.
So this is a question about some I remember during I guess one of the compilers used to have very helpful diagnostic information, and I think in one of the slides you mentioned, is there a particular compiler option for LLVM that can tell us if we are missing out on something, like if some loops are not vectorized or something like that?
So I mentioned previously you have all those -rpass. You need to enable those explicitly. If you just want to get everything, there is, I believe, a option called like -f save optimization record. And what that will do is give you a giant YAML file for like every single optimization. And then there's other like tools in tree for LLVM that will then let you use that optimization record to like view it in your web browser with your source, and it'll like annotate like, oh, this loop had these remarks and this hotness if you used PGO and stuff like that.
Ah, that's cool. Thanks. I'll look into it. But typically the right option would be the rpass options.
Yeah, just rpass.
Thanks, Joseph.
If you just want everything, -rpass takes a regular expression, so I think you can just put like a .star or something there, and I'll just get like literally everything, but I wouldn't recommend it.
Oh, I see. Cool.
There's on that note, the tooling that Joseph mentioned, where you get all of the remarks into a YAML file. Once you did that, you can actually overlay it with your source code. There's actually two different tools that allow you to overlay the remarks in your source code, and then you can scroll through your source in a browser, and it has like bubbles or something on the side where it tells you all the remarks for a particular piece of code associated with it. And again, that also is composable with the hotness such that you can limit it to hot pieces of code, for example.
Yeah, and if anyone like runs into a problem they feel like should be a remark, you can probably bring it up and someone will add it.
Last 5 minutes. Okay, then let's give people the 5 minutes back so they can get coffee and whatever else. I hope you have a great rest of your day. Thanks everyone for coming in. Feel free to reach out to all of us. Again, we have the bi-weekly office hours for LLVM in OpenMP. We have the weekly LLVM in OpenMP and LLVM meeting. GitHub issues for OpenMP, and then the discourse for LLVM. All good ways, in addition, obviously, to email. You'll find our email.
Okay, thanks. Bye.